Hello, hello. Hope I'm audible. So today we're going to continue reading the paper Monosemanticity. So yeah, the last stream was very short. I shared only a few parts. Today, now hopefully we'll complete it. So before all that, just ensuring that the audio is fine. Looks good. Right. So where were we? We were talking about monosemanticity, how normal neurons are polysemantic, and with multiple mean one idea or one feature corresponds to multiple neurons in a neural network, in a neural network layer. So one feature corresponds to a linear combination of neurons in a layer. So we don't want that. We want neurons per layer. So that is what this paper is trying to do, making the neural network monosemantic. Okay, cool. Summary of the result. Sparse autoencoders work very well, right? They they produce interpretable features that are effectively invisible in neuron bases. We find features quantifying and Huber script that are not active in any of the top dataset example for any of the neuron. Sparse autoencoder feature can be used to intervene on and steer transformer generation. Okay, cool. Sparse autoencoders produce universal features. This is kind of interesting, right? Sparse autoencoder extract laterally monosemantic features very well. We can also add they extract universal features. Cool. Features connect in finite state automata like system that implement complex behaviors. For example, we find that work together. We find features that work together to generate valid HTML. I mean, we'll see that. Problem statement. Problem setup. A key challenge in our agenda of reverse engineering neural network is the curse of dimensionality. As we study ever larger models, the volume of the latent space representing the model's internal state that we need to interpret grows exponentially. I mean, yeah, obviously. We do not currently say a way to understand, search, or enumerate such a space unless it can be decomposed into independent components, each of which we can understand on its own. In certain limited cases, it is possible to sidestep these issues by rewriting neural networks in a way that don't make a reference to certain hidden state. In certain limited cases, it is possible to sidestep these issues by rewriting neural networks in such a way that they don't make reference to certain hidden states. For example, a mathematical framework for transformer circuit. What is that? What is that? Is it a paper? Is it a book? Oh, it is an earlier paper or earlier blog paper thingy. We were able to analyze one layer attention only network without addressing this problem. What problem? Scaling. But this approach becomes impossible if we consider even a simple standard one layer transformer with an MLP layer with ReLU aggregation function. Understanding such a model requires us to have a way to decompose the MLP layer. Okay. In some case, this is the simple language model we profoundly don't understand. This is the simplest language model we profoundly don't understand. And so It makes a natural target for a paper. We aim to take the MLP activation, the activation we can't avoid needing to decompose, and decompose them into features. So, I mean, in the Monosemanticity paper, which activation is used to train the SI? What I meant, okay. I meant which activation layer is used to train. Logic lens activation, the pre-softmax logics from the GPT-2 model. GPT-2 model? What do you mean GPT-2 model? Okay, so we take the very last, what do you call it? Logics. What is the difference between logics and activation? They're the same, right? Different part. Activation are the output of intermediate layers of a neural network after applying respective activation functions. Okay. Logics are raw unnormalized output of the last layer of the neural network just before softmax. Okay. So, what do you call it? So, we can say that logics are activations, right? That's correct. Logics are a specific type of activation, namely activation on the final layer before applying normalization function like softmax. All logics are activations. However, okay, sure. Cool, cool, cool. Unbounded real number. Bounded depends on the activation function. Okay, cool. Crucially, we decompose. Just ensuring what is fine. Okay, okay. I thought audio was okay, cool. Crucially, we decompose into more features than there are neurons. Obviously, this is because we believe that MLP layer uses superposition. And I have to read the circuits, all the circuits blog, right? To represent more features than it has neurons, and correspondingly do more useful non-linear work. We believe that the MLP layer likely uses superposition to represent more features than it has neurons. MLP layer likely uses superposition to represent more features than it has neurons and correspondingly do more useful non-linear work. Okay, in fact, your largest experiment will expand to have 256 times more features than neurons, although we'll primarily focus on a more static expansion. Uh, okay, but these features are like there are millions of features, like billions of features, right? Like dogs, cats, and all of them features literally. layers. Uh, One attention block, one MLP block with value MLP size 512. Okay. First atom card one value, one linear. Give me a sec. 1 second. All right. Sorry about that. Crucially, we decom MLP size is a lot. Data set the file. Transformer MLP activation. What is the file? Mm-hmm. Comment practice on the same data model. Each generator and different number of equals according to the perceived quality of the data. Table below show the relative size. Hmm. Hmm. Okay. Two copies of the file round using DMC and teaching building copyright act. Users responded by creating copies of the file. The offending content removed. Hmm. Okay. This is it. What is the size of the data set? Mm-hmm. Okay, so what are converted paracket from? First page. Mm-hmm. Right. In the following subsections, we'll modify the setups at one more length. Additionally, A more detailed discussion of the architectural details and training of these models can be found in the appendix. Features as decomposing. There is significant empirical evidence suggesting that neural networks have an interpretable linear directions in activation space. This includes classic work by this person, linguistic regularities in continuous space word embeddings, investigating vector arithmetic in word embeddings, and similar results in the latent spaces. There are also large bodies of work investigating interpretable neurons, which are just basis dimensions. Okay. Okay. A longer review can be seen in the smaller strength. Okay. And if linear directions are interpretable, it's natural to think that there is some basic set of meaningful directions which more complex directions can be created from. If linear directions are interpretable, it is natural to think there are more basic set of meaningful directions which are more complex directions. Which if linear direction is interpretable, it's natural to think that there is some basic set of meaningful directions which more complex directions can be created from. Okay, what does that mean? We can. Uh-huh. Okay. We call these direction features, and they are what we'd like to decompose the models into. Okay, they are defining features. Sometimes, by happy circumstances, individual neurons appear to be the basic interpretable unit, but quite often this isn't the case. The aspiration of interpretability in neural networks. Linear directions are interpretable. Neural networks often encode information in linear directions within their high dimensional activation space. If these directions are interpretable, it suggests that they represent some meaningful concepts or features. That's also true. So, what is the point of the paper? What is it that the paper is trying to achieve? Don't say interpretability. Aims to explore and improve. Okay, sure. I want specifically what? Neural network process input and encode information as higher dimensional activation or features. Neural network process inputs and encode information as higher dimensional activations. Okay, that makes sense. The paper investigates whether these features can be understood as simple interpretable units, as individual neurons or directions in activation space. Neural network process input and encode information as higher dimensional features. Hmm, okay. It seeks to determine when and why some direction in activation space correspond to meaningful monosemantic features. Features that represent a single interpretable concept. Characterizing superposition. Neural networks often use superposition to represent multiple concepts stored in the same neurons or direction. This makes interpretation difficult. The paper aims to analyze and quantify superposition, not to change it, which is interesting. Okay, I mean, if you interpret it, you can probably align it, right? Eventually, maybe not today. Sparse and interpretable representation. Paper proposes and investigates methods such as sparse autoencoders to find more sparse, detangled, and interpretable representation of features in model. Developing tools for mechanics, blah 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 blah. I mean, tell me specifically what this paper is trying to do. Is it trying to use psi to make each feature correspond to exactly one neuron? Also, what define feature with respect to this paper? They are not explicitly trying to make each feature correspond exactly to one neuron. Okay. Instead, paper aims to understand and disentangle features within neural network representation by exploring whether they can be made interpretable and monosemantic. It uses techniques like psi to isolate linear directions that represent specific meaningful concepts. Honestly, I don't understand. And that's fine. Features features is in the network legend space can be made sparse or distangled. Superposition can be reduced or interpreted even if the features are not aligned with individual neurons. Techniques like psi can provide better mapping. The context of the paper, a feature is a linear direction in the higher dimensional activation space of the neural network that corresponds to some meaningful interpretable concept or property. A feature represents the presence of specific object or attribution like concepts like cat, striped texture, emotion in language model. Features are the building blocks and can be monosemantic, be distributed. Multiple neurons combine to represent one feature. Exist in superposition. Multiple features overlap in the same neuron or direction. Yeah, they can come in any form or fashion. Okay, we are trying to make them non-overlapping. Okay, that's the concept. So, okay, let's think. What is the paper is trying to do? We have a neural network. The neural network is not monosemantic. It is what is the other word? Polysemantic, huh? Probably. It is polysemantic. So let's take a concept. Let's say cat. That's a feature. What is a feature? It is a direction in the neural network which represents one idea or one concept. So cat. Now, multiple neurons. So when there is the cat in the context or something like that, multiple neurons activate together. This is polysomatic. That is one. That can be one case. Another case is that, yeah, that is one case. I mean, that is the main case. When we activate dog, again multiple neurons activate and they can coincide. What we are trying to do is to minimize this number of, what's it called, coinciding things. Okay. Okay. Okay, the primary purpose of the paper is to disentangle the goal of this paper is to make features what is it called, disentangle. This means that the few neurons, mean each feature should correspond. Oh, each feature should correspond to a single concept. This is important because it makes model more interpretable and easier to understand. Okay, features can also mean multiple things, right? Mm. Okay, so I think what the word feature means is a concept that a few neurons together make, and this concept can also be polysemantic. Okay, 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 okay. Mm. So what are we trying to do? How can we do it? Should be should refer to a single key idea. Also, a few neurons. Also, the neurons that activate during when we talk about this feature should be okay. Hmm. So first we need to define features. Okay, so if I'm trying to like literally do this thing on let's say GPT-2, what should I do? How should I do it? Right? That's the important question. So, hmm, let's see. We can ask GPT-2. We can extract the very last features from GPT-2. Then what? We can give those features to Sai. Then we have a Sai, which will be very polysemantic. Then what? We want to make I mean, first we have to define features, but fortunately for us, features appear to be, I mean, features autoencoders produce relatively universal, sparse autoencoders produce relatively universal features. This probably means that we can copy paste the features from other people who have done this. I don't know if that is exactly what that means, but wait, we'll see. Learn the neurons, 512 hours. Okay. Okay, so they defined when this activation, this neuron activates, right? Top activations, brain count. I mean, instead of doing this, how about we like store what like let's say we are training the sparse autoencoders. What if we during training the model we mark each neuron, hmm, and we kind of not which neurons are like back like, which neurons are trained when we do back propagation, which let's say one context length of tokens. I don't know, man. I have no idea. Hmm. Monosemanticity pa- paper implementation. This is reference 50 file scale in Monosemanticity, which is an open source sparse encoder that has been trained on GPT-2 was significantly smaller than Llama. They even implement the recreation of the entropic feature dashboard. You can identify the neuron. The clamping is trivial. Give me a second. All right. Up I'm audible now. So we are publishing a set of 12 sparse outbound products for GPT-2 small residual streams. These dictionaries have approximately 25,000 features each, with very few dead features, and high quality reconstruction when the actions are replaced with output 3.3. Readers can access sparse outbound encoders in this repo. 25,000 features, that means 25,000 key idea. As we use an expansion factor of 32, I will on the residual stream, dimension of GPT has different features. Dimension. We trained with element coefficient of which is refilled and shuffled when our 50% of the tokens are used. To avoid dead neurons, we use ghost gradient. What are ghost gradients? Hmm. Okay, we'll look into it. So these are actually trained SAI for GPT-2, right? So how ideally, I can just use it, right? The L0s range from 5 in the first layer to 70 in the ninth layer, increasing by about 5 to 10 per layer and dropping in the last two layers. L0 means L0 loss, right? What is L0? Oh, it's not from either. L0 norm is a mathematical concept that quantifies sparsity in a vector, essentially counting the number of non-zero elements with it. Okay, so L0 determines if I so lower L0 means that the matrix is sparse. Hmm, right. Yeah. Okay. 5 in the first lab to 70 in the ninth lab, increasing by about 5 to 10 per lab and dropping in the last two layers. Okay. Hmm. Okay, I kind of want to read this. Yeah. But we will continue in the paper now. Though. Yeah. Mm, all right. In the if the linear directions are interpretable, it is natural to think that there is some basic set of manifold directions which more complex directions can be created from. Okay. Oh, these are called features. So hopefully, ideally, like we can have an animal feature and dog feature will be kind of related in some way to animal feature, right? We call these directions features, and they are what we like to decompose models into. Sometimes by happy circumstances, individual neurons appear to be the basic interpretable units. Quite often, it's not the case. So we don't care about making neurons like individual. Like we don't want in the side, let's say for a feature as a cat, we don't want we don't necessarily want one neuron to represent cat. We are fine with many neurons representing cat. We just want to identify the concept of cat and identify that these neurons together, the linear combination of these neurons refer to the concept of cat. What I said last was kind of what do you say, was not what I thought I would say after reading this, but I think that is correct, but I don't know if I am. I'll try this. So what this paper is trying to do is to find the features that the neural network makes. These features will be the linear combination of neurons in the neural network. Aims to find and understand features that are neural network and that a neural network encodes in the activation. These features are conceptualized as linear combination of neurons in the network rather than being tied to individual neurons. Okay, I'm taking you. Thank you. I'll have you somewhere here. Key points. Features in the neural network. Cat. Negotiation. Stripe protector. A feature is a linear direction in the activation function that corresponds to a meaningful concept or property. I also want you, sir. I place you here. Yes, why not? Features are often represented by linear combination of neurons. Okay, so that is a new neuron. Our point in this paper is to find features and the neurons they correspond to. Objective of the paper to identify feature in the latent space, analyze whether these features can be made monosemantic. Study and potentially reduce superposition where multiple features overlap with the same neuron direction. Okay, cool. I also will take you. Right. We call these features. Uh, if linear directions are interpretable, it is natural to think that there is some basic set of meaningful direction, which more complex directions can be created from. Hmm. Sometimes very happy circumstances, blah 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 blah. Okay. Instead, we decompose activation functions as the combination of more general features which can be any direction, where xj is the activation vector and this f of x is the activation of feature I, and b is the bias. Note that this decomposition is not new. It's just a linear matrix factorization of the kind commonly employed in dictionary learning. Okay, we spread this neuron feature. In your sparse autoencoder setup, the feature activations are output of the encoder. The feature activations are the output of the encoder. So what is this wx plus p? We take the value. Okay. W is the weight matrix. B and D are pre-encoder and encoder bias. We feature the feature directions of the column of the decoder weight matrix again. If such a sparse decomposition exists, it raises an important question. Are models in some fundamental sense composed of features, or are features just a convenient post hoc description? Are models in some fundamental sense composed of features, or are features just some convenient post hoc description? In this paper, we take agnostic proposition. What does agnostic position mean? I think it's neutral. Oh, okay, my bad. Believe the existence of a higher power such as God is either unknowable or unknown. Okay, okay, so we think that this is unknowable. The answer to this question or unknown. The other results of the features universally suggest that the features have existence beyond individual models. True. That would be helpful for us. Superposition hypothesis. Man, the paper is so long. I've been reading for so long and it's not even cost. Sorry. Superposition hypothesis. To see how the decomposition relates to superposition, we recall that the superposition hypothesis postulates that neural network wants to represent more features than they have neurons. Sure. We think this happens by kind of noisy simulation. A small neural network exploits feature sparsity and properties of higher dimensional space to approximately simulate a much larger and sparser neural network. To see how the decomposition relates to superposition, we recall that the superposition hypothesis postulates that the neural networks wants to represent more features than they have neurons. We think that this happens by the kind of noisy simulation where small neural network exploit feature sparsity and properties of higher dimensional space to approximately simulate much larger and sparser neural network. Small neural network exploit feature sparsity and properties of higher dimensional spaces to approximately simulate much larger sparser neural network. I don't know what that means. But what I'm thinking, we think this happens via a kind of noisy simulation where small neural network exploit feature sparsity. What is feature sparsity? The features are sparse and properties of higher dimensional spaces to simulate larger sparser neural network. I don't know what that means. Hypothesis of rectangle model, observed model. Under superposition hypothesis, neural network we observe are simulations of larger network where each neuron is rectangular feature. Oh, okay. So you're saying that for every neural network, there is a higher neural network where the features are rectangle. Cool, that makes sense. These idealized neurons are projected on the actual network as almost orthogonal vectors over the neurons. Sure. The network we observe is a low dimensional projection of the larger network. From this perspective of individual neurons, this presents as polysemanticity. Okay, cool. That makes sense. I kind of want this. Nice. A consequence of this is that we should expect the feature direction to form an overcomplete. What does overcomplete means? It's a linear algebra concept that describes a set of functions that is larger than basis. A system is called overcomplete if it contains more vectors than necessary to be complete. There can be removed from the system such that it remains complete. A consequence is that we should expect the feature directions to form an overcomplete basis. That is, our decomposition should have more directions than neurons. Or rather, the feature ideation should be sparse, because sparsity is what enables kind of noisy simulation. This is a mathematical answer to the classic problem of dictionary learning. Okay. Like I kind of want to know what a dictionary learning is also. So, what is dictionary learning? Type of machine learning techniques amplifying sparse representation of input data. Okay. We attempt to find a sparse representation of input data. Cool. Okay. What makes a good decomposition? I think I'll just stop here. I'm getting tired, man. This is very in the paper is painful. Yeah, I'll stop right now. Never have I felt this kind of. Yeah, we'll stop now. Thank you for watching.